the session A1, Autonomous Driving Systems. And the first talk of this session is SLEMI Equivalence Modulo Input-Based Mutation of CPS Models for Finding Compiler Bugs in Simulink by Chaiful Azem Chowdhury.
Thanks, Dongan. Can you hear me?
Yes.
Awesome, thanks. And welcome everyone to our talk on Equivalence Modulo Input or EMI-based mutation of cyber-physical systems, CPS, models to find compiler bugs in commercial toolchains like Simulink. So when designing complex cyber-physical systems, engineers would often design them as graphical data flow models, for example, this Simulink model, so that they can simulate them in commercial toolchains like Simulink and automatically generate code, executables, and deploy them in the target hardware. Now, a bug in the toolchain can propagate to subtle bugs in the artifacts that are automatically generated, which may have catastrophic consequences. So in order to make sure that safety critical systems do not fail because of cyber-physical system compiler bugs, one approach commonly followed in the industry is to use automated testing. And here I'm giving an example of automated testing, which is randomized differential testing. This has been proven very effective in finding compiler bugs in production-grade compilers like GCC, LLVM, and also cyber-physical system toolchains like Simulink. So the idea is that we have a CPS model generator which can automatically create valid Simulink models. Then we take one such valid Simulink model and compile and execute it using two different compiler configurations, for example, optimization on and optimization off. Now, since we are compiling, executing, and measuring the output of the same model using different optimization settings, their outputs should be same. If it's not same, it means that we have discovered a compiler bug. Now, quick background on Simulink models. So models are comprised of blocks. For example, here, this add one block takes two inputs and just sums them up. Next, to establish the connection between blocks, we can have directed connections as shown in this figure. Now we can drag and drop these blocks from standard libraries provided by the compiler toolchain, or we can also design our own custom behavior using native code like C. Then instead of designing flat models, engineers prefer to design models in hierarchies. For example, here this action one block is comprised of other Simulink blocks. And next we have conditional execution. For instance, this if block can trigger either of the action one or action two block, depending on the input it's receiving. Then blocks have certain data types, and this is specified in the official documentation. For instance, here this difference block can support double, single, int 8, or so on. And we can explicitly specify the data types of each blocks, or we can just ask Simulink to inform the data types for us. Next, one key difference between cyber-physical system models and procedural code like C is this explicit notion of execution and simulation. For example, CPS models are simulated over a fixed duration of time, and we can also explicitly specify when to calculate a block's output. This property is commonly known as sample time. And this can be either explicitly provided for each block or can be inferred automatically by the toolchain. Now we compare our tool SLEMI to SL4, which is the state-of-the-art differential testing tool for Simulink. So it can automatically generate valid Simulink models, and then it uses them for differential testing. So this is good. This found some new compiler bugs in Simulink, but it's actually very computationally expensive to create valid Simulink models from scratch. Now, quick background on equivalence model input-based testing. This is the idea that we use in the paper. So instead of plain differential testing, where we just take a model and compile it in two different compiler configurations, now we take one Simulink model, we call it seed, and introduce a small change and call it a mutant, such that the seed and the mutant are functionally equivalent. So since they're functionally equivalent, when we compile and execute and compare their output should also be same for a fixed input. And if it's not same, then it means that we have also found a compiler bug. And the idea was first surfaced for procedural languages like C, where we take a C code as seed and then profile it to find the dead and live regions in the code. And then we can introduce small changes in the dead and live regions to create valid mutants. Now, there are some key differences when we try to do EMI in CPS compared to C programming language. For example, in CPS, there is this notion of zombie blocks. We coin this term. These blocks have properties of both live and dead blocks. For example, here, the if block is always triggering action 2 to execute. That means action 1 will never be executed, so it has properties of dead blocks. However, it is also sending output to other live region in the code. That means it has property of live code as well. So we coin these blocks, zombie blocks, and they have to be treated carefully when we are doing mutations in CPS. Now, a quick overview of the overall approach. We have a collection of seed models that we want to mutate. So they can be automatically generated by SL Forge, or they can also come from third-party models created by humans. So we have a corpus of these models, which we call seed, and then first we perform some one-time base mutations and collect coverage from the seeds. This is done only to improve the efficiency of the tool. We cache these intermediate values, and then we perform EMI-based mutations in dead, live, and zombie regions of the model. And then we do differential testing. If we have found a bug, we report it to the compiler vendor. And if they say that it's indeed a bug, we mark it as a true positive. Otherwise, it's a false positive. And this typically means that the specification was not very clear at the first moment. So to summarize, EMI for CPS introduces new challenges. For instance, we have to deal with zombie blocks. We have this explicit notion of time, which we don't have in C. And also compared to C language, we don't, it's more difficult because we have advanced tools and features like data type and sample type inferences. Now, a quick pseudocode of our tool. So it takes a type annotated seed model, and first we randomly select a block to mutate. If it's a zombie block and it's deep inside in the hierarchy, we just delete it and connect its predecessor to its successor. Otherwise, if it's the top level, we cannot just delete the block. We have to ensure that we can replace it with a block which mimics its output. Lastly, we also introduce changes in the live regions. For example, we change the hierarchy, or we take a block and enclose it in an always true or always false branch to create equivalent models. Now, how do we evaluate our tool? First, we wanted to make sure that SL EMI is more efficient than SL Forge. So we randomly generated 500 seed models from SL Forge, which are comparable to the non-trivial models that humans actually create. Then we check the runtime. So SL Forge takes about on average 470 seconds per model, whereas our tool EMI only takes 46 seconds to create a mutant. That means we can create more mutants given the same runtime, and our tool is likely to find more bugs. So then, did it actually find more bugs or found any bug? Yes, we have so far reported 14 bugs, and 10 of them were confirmed by the toolchain vendor. And our false positive rate is also low; it's only 2. Lastly, does EMI add more value compared to just vanilla testing by SL Forge? To compare this, we gave the two tools similar compute and found that SLEMI has found more bugs than SL Forge. That means it can likely find bugs that were initially missed by SL Forge. Before concluding, I'm just giving one demo of bug that we found. So on the top row, we are seeing a snapshot of a model, and then we mutate it to the one in the bottom. And the highlighted blocks are same in the seed and the mutant. So this was a zombie. This was inside the nested zombie region. So we could just delete the blocks and connect it with the equivalent type. And this should be the seed and the mutant should be same, but it was found not same, as it triggered a compilation error. And Mathworks confirmed that it is indeed a bug. So thank you. And our tool is currently released as open source, and we are welcoming any contributions. Thank you.
Okay, thank
I'm
you.
open to questions. Thanks.
Yeah, thank you for the presentation. Since I don't have any questions from the audience, maybe I can raise some questions.
Sure.
Yeah, I noticed that there is some little case of false positive. Of course, the approach works very nice, but there could be some false positive in this case. Then, can you explain why this happens in your case?
Yes, so this sometimes could happen because we did not clearly understood the specification of the toolchain. For instance, for C, we have a clear grammar, so it's very unlike that. So it's easy to create valid C code. However, for commercial tools like Simulink, they are often so big and they're commercial. That means their source code is not released. So sometimes the specifications are ambiguous, or sometimes there is also bug in the specification. So that means that we did not clearly understand the specification. So we are trying to create a valid mutant, and we thought that it was a valid mutant, but when we communicated the result with the toolchain vendor, it turns out that there was a bug in the specification. So mostly these false positives are coming from those kind of those bugs in the specifications. We actually find it also very useful because specifications should be very clear, and there should not be any bug in the specification as well. So in this process, we are actually also contributing to better specifications of commercial things.
All right.
Does it answer your question?
Yes, it's very, very nice answer. Thank you very much. Thank you. And I think it's the time to move on to the second presentation. Okay, second talk is Deep Billboard Systematic Physical World Testing of Autonomous Driving Systems from Kong Liu.
Hello, everyone. Today is my great pleasure to present our work at the ICSI virtual conference. And the title of our work is Deep Billboard Systematic Physical World Testing of Autonomous Driving Systems. So due to the advancement of machine learning techniques and the embedded system hardware, autonomous computing is a hot concept being pervasively applied in different domains. Here I show several: transportation, drones, robotics, and medical cyber-physical systems. So among these domains, autonomous driving seems to be a very promising application. So here I showed a state-of-the-art autonomous driving systems where we're utilizing a set of hardware to capture data and computing, analyzing this data through the Linux operating system and the robotic operating system middleware. And then we're applying state-of-the-art end-to-end driving application software like AutoWare I shown here. Okay, so basically what AutoWare does is for each captured image, it will utilize a set of DNN modules like localization, detection, trackings, which are mostly driven by deep neural networks. And then through analyzing the real-time captured environmental data, the computing system employed in this vehicle will be able to make control decisions like motion planning: should I brake, should I accelerate, or steering. So the deep neural networks actually is enabling such autonomy in driving to a very large extent. So here I showed an end-to-end driving DNN-driven autonomous driving solution, which is first proposed by NVIDIA. So this solution, end-to-end method, is very powerful because by utilizing a set of CNNs and RNNs, the driving framework is able to kind of learn and mimic the behavior, the driving behavior of human beings under different road conditions. So because of the safety criticalness of the autonomous driving, so the robustness and safety testing, okay, becomes a very important topic, particularly given that recent set of research has shown that machine learning algorithms and DNN in particular are very vulnerable to adversarial attacks. So the result is that the DNN models, like for example steering, will not be able to make correct control decisions like the steering angle. So the goal of the robustness testing in software engineering is trying to identify adversarial scenarios. And indeed, there has been a recent rich set of works on digital world testing, where we try to generate digital world perturbations and to come up with artificial driving scenarios to enrich test suite. For example, the left three figures shown here is that where we generate digital perturbations and then apply it onto different road scenarios, and then try to come up with new driving scenes to see whether the autonomous driving system is robust under such settings or not. And some other recent work are trying to make such testing cases to be more realistic and diverse, like the two figures I showed.
Something happens
on the right-hand side. Okay. Unfortunately, what we have seen so far in this testing effort, it happens all in the digital world setting. So this is the major motivation behind Deep Billboard, where we find a critical missing piece on autonomous driving testing, where we have to understand and exploit both digital and physical adversarial perturbation generation for impacting driving decisions. And in this paper, we focus on the steering module. So in other words, such the digital world perturbation generated like we have seen here cannot be implementable in practice in physical world, right? There's no way for us to generate these small black dots and then paste it onto the sky, right? Which is our background imagery. So physical world, how to do physical world testing of autonomous driving systems is the major motivation behind Deep Billboard. Okay, so we present the solution, Deep Billboard, which is a systematic physical world testing of autonomous driving systems. And in order to implement it in the physical world setting, Deep Billboard targets at a very common and practical driving scenario where a vehicle may drive by roadside billboards. Like an example is shown here. It's very common for us to see such advertising space available on the roadside, and we can just call the phone number, and then we run this space, and we can put whatever contents or image onto this billboard. Okay, so the goal is definitely to generate a single printable image, which can be physically printed out and also pasted onto this roadside billboard target. And we want this single image to continuously attack the driving by vehicles, because again, the driving by process is a continuous process involving multiple image frames, not just a single frame. So there are many challenges, and I list which can be categorized into either physical world or technical issues. So physical world issues are very intuitive. For example, only billboard area could be manipulated, right? So this is different from the digital world testing, where the entire image input, you can add perturbations to wherever you like. Okay, so this is not possible under the physical world setting. Also, the background imagery is also moving during this driving by process. And also the perturbations we generate under the physical world, the methodology has to survive under different conditions, like lightning conditions, and also must be perceptible by the sensing hardware and printable. Okay, so there are several key technical challenges, but a key technical challenge herein is that because the driving by process involves multiple frames, so all frames in this driving by scenario has to be considered in order to generate globally maximized attacking effects, because this is our technical goal, right? We want a single perturbation to continuously impact the driving by autonomous vehicles. So here shows a very general workflow of the Deep Billboard, and details can certainly be found in the paper. So basically, we're trying to identify the coordinates of the targeted roadside billboard within each capture image during this driving by process. And then we feed this input into the DNN model, and we apply a joint gradient optimization algorithm, which is the key algorithmic component in Deep Billboard in our design, to generate an adversarial pattern which can continuously impact the driving vehicle. Okay, so here is the general process. So we first, for each single image frame, we generate a locally best perturbation. And then we try to find a globally optimized single perturbation that would mislead the DNN driving model the best in a continuous manner using this joint loss optimization method. And this method considers dynamic driving conditions and some other physical world dynamics. For example, this algorithm also enhances perturbation printability by transferring these RGB values to printable colors. So again, more details could be found in the paper if you are interested. So regarding evaluation, we have done a comprehensive set of experimentation involving popular self-driving models like the DAVE models proposed by NVIDIA, and know that these DAVE driving models have been intensively tested by NVIDIA by driving millions of miles and incurring almost zero accident. And we also test the another popular self-driving model, which is Epoch from the Udacity challenge. And regarding the image datasets, we applied the Udacity, DAVE, and Kitty driving datasets, which are all popular and widely studied datasets for the self-driving scenario. And regarding the video datasets, we grab YouTube driving videos as well as the videos recorded by our own camera of a driving car when we drive by a roadside billboard on UTD campus when we conduct these physical world implementation and case studies. So here shows the digital world evaluation listing the predicted angle error under different data set and different road conditions. So here I just highlight 4 examples. As you can see here, we use deep billboard to generate a single perturbation, a single adversarial image, and we digitally apply it onto the corresponding area of this roadside billboard. As we can see here, the predicted angle error is actually, the angle error is actually pretty noticeable, right? From 7 to almost 25 degrees. So as reported by the transportation agent sector, if a vehicle, if the steering angle error becomes 3 to 5 degrees and lasting for more than 1 second, then this is considered as a very dangerous driving behavior, which may result in accidents. Okay. So regarding physical world evaluation, here I show 2 case studies where we print out 2 adversarial images and we print it out and paste it onto the roadside billboard, and we conduct this experimentation within the UCD campus. And basically, we drive a vehicle bypassing this roadside billboard, and we record the resulting angle error for each captured image frame. So this figure summarizes the results, where the x-axis denotes the frame index, the y-axis denotes the angle error. As you can see here, the angle error for all frame index are pretty noticeable, ranging from 5 to 10 degrees to almost 40 degrees. So here, the interesting observation is that whenever the frame index increases, the steering angle error also becomes larger. So this is very intuitive, because when the frame index increases, it implies that the vehicle actually drives closer to this roadside billboard. So this adversarial billboard would impact the DNN optimization process a lot more compared to a far distance. Okay. So finally, I would like to show a video demo regarding how we conduct one of these physical world case study. As you can see here, we're basically driving on a straight road. However, the red arrow indicates the actual steering angle predicted by the DNN steering model in a real-time fashion within each image frame. So as you can see here, right? So the predicted steering angle is actually had encountered a very large error compared to the correct steering angle, which should be just straightforward. Okay. Okay. Thanks a lot for listening to this talk. So basically, we present the billboard, a systematic physical world testing of autonomous driving systems, and a set of immediate future work we plan to conduct is to extend and apply the billboard using onto a set of realistic vehicles. Like right now, we're trying to implement the billboard using Tesla, and we're trying to see during an actual autonomous driving process, what is the efficacy of the billboard. Okay, thank you very much.
Okay, thank you for the good presentation. I think we have a question from the audience. One anonymous, the audience says, do these inputs applied continuously cause actual car crashes? Can you answer?
Right, so I think the question is, so actually we also conducted a on-policy evaluation, meaning that Wait, so he asked me to start video. Okay, so actually, we conducted a ARM policy evaluation, meaning that at each image frame, we kind of real time manually adjust the steering angle according to the predicted steering angle made by the DN model. So actually, it will be able to continuously mislead the control action.
Okay, thank you for the answer. I think we have to move on to the next talk.
Okay.
Thank you again. Yeah, thank you again for the good presentation, Kong. And the next presentation is titled Misbehavior Prediction for Autonomous Driving Systems, which is presented by Andrea Stocco.
Thanks for the nice intro. I'm very happy to be here today to present you our ongoing research on predicting misbehaviors in DNN-based self-driving cars. The technology we are witnessing behind self-driving cars has matured to the point that advanced driver assistance systems, such as lane keeping, are standard on a number of vehicles. However, developers who have to test the reliability of the systems are tackling unprecedented challenges. Testing a DNN that performs the task of driving is indeed quite laborious. First, human drivers drive camera-equipped cars and record driving data, such as images and other driving commands by the human driver. All this data is then used to train a neural network for behavioral cloning. Once the model is trained, it is further tested on simulation platforms, and it is finally deployed on a real car to be further tested in the field. In this research, we explored some of the challenges that await developers who are attempting to qualify fully autonomous vehicles for large-scale deployment, particularly devising a technique to perform online misbehavior prediction. But what is a misbehavior for this kind of software? Misbehaviors can be defined in many ways and are necessarily domain-specific. For lane-keeping component, the misbehaviors we studied are defined as the car going off-road or crashing with other objects. However, during the operation of the system, the DNN will always output a prediction, regardless whether the input is supported, known, or unexpected, similarly to the works just presented in this session. However, I want to argue that we cannot fully assess the reliability of a DNN-based autonomous driving system if we study the model in isolation, because we need to observe the causal effects of multiple wrong predictions on the final driving quality. And that can be done only in field or more conveniently through a simulation platforms. In the context of our research, we used the Udacity simulator for self-driving cars, which allows to connect a deep neural network that imitates the driving behavior. However, if you are implementing a system of this kind, it is virtually impossible to account for all driving conditions at training time, because there will always be that one situation that is unknown and that might cause the car to misbehave. The first contribution of this research is that we modified the original Udacity simulator to inject weather conditions such as snow, mist, and rain in a controllable way that can be used to test the system under adverse conditions. Another component automatically records the status of the car with the environment. In this way, we can record labeled datasets in which, for each frame, we know whether the car is on or off-road or whether crashes happen. The main objective of this research is to try predict whether a car is facing an unsupported scenario before the actual misbehaviors are observed. And our main approach revolves around monitoring the unexpectedness of the driving scenario. Suppose this self-driving car was trained only on sunny driving condition. As such, we need to devise an unexpectedness metric that is low when the scenario is known, and it is instead high if the conditions are unexpected, for instance, when it is suddenly raining. Our purpose then is to automatically set a threshold to determine when the unexpectedness is raising over an acceptable level. In practice, our approach consists in a redundant component that analyzes the data fed to the car. In the face of a potentially dangerous situation, the driver can override the main driving component and recover to a safe state. This architectural pattern can be especially advantageous if the monitor can be made substantially simpler than the actuator. However, this is not an easy task because the combination of adverse events and driving conditions are simply too many to be enumerated in a classical written requirement specification. For this reason, we need an architecture that is fast at making predictions and that can be trained with the largest amount of data available. As a core component of our technique, we rely on autoencoders that are neural networks whose task is to reconstruct the input that are given with high fidelity, as measured by a distance metric such as the mean squared error. The rationale of using autoencoders for anomaly detection is that we can train them with the same data used for the driving models. Thus, the predictor will be able to reconstruct well inputs that are similar to the ones they were trained with, whereas they will fail to reconstruct inputs that are unseen, hence potentially unsupported by the car. Here's a video of our autoencoder-based anomaly detector applied to the Udacity simulator case study. The car here is driving on nominal context, and you can see the unexpectedness score is quite low. However, in these other videos, we can see instead that the detector is active because the context is unsupported and the unexpectedness is quite high. We studied different autoencoders architecture within our framework, which we called self-oracle, and compared them with the input validation strategy of DeepRoad, which is based on a combination of feature extraction and PCA. Let's now have a quick overview of the experimental study and the main results. Our experimental setting consists of different tracks and weather conditions. We use the sunny condition as nominal and study the effectiveness of self-oracle in recognizing several hundreds episodes in which the car was facing an unseen condition that ultimately led to a crash or an out of bound. Thus, the main research question revolves around the effectiveness of our technique. And in brief, our results show that self-oracle is more effective at predicting misbehaviors with approximately a factor of 3 over the existing DeepRoad technique when the ratio of accepted false positives is set to 5%. Another notable result is that the correct misbehavior predictions are made 6 to 9 seconds in advance, which is quite enough to enable self-healing mechanisms, either by the driver or by another component. So just to conclude this overview, I presented you self-oracle, which is a promising technique that uses autoencoders to perform online misbehavior predictions for autonomous driving systems. And the main highlight of this research is that it proposes the use of autoencoders and their reconstruction loss as a useful score to measure the unexpectedness of the driving scenario. Particularly in our experiments, the variational autoencoder proved to be the best. So if you want to know more, feel free to read our papers and download our tool and simulation platforms. It's all available for you to use and enjoy. And I thank you for the attention, and I'm glad to get your questions. Thank you.
Okay, thank you for the nice presentation, Andrea. It's a very interesting talk. We have several questions from the audience. I will let you know. The first one, the most voted one is, you trained your model using synthetic weather conditions in a simulator. How well does this training apply for real-world conditions?
Of course, our results are subject to the threat to validity in terms of generalizability, because our results are as valid as the simulation platform is able to reflect the real world. So this is actually a good question, and we asked the same question ourselves many times. And the reason why we use the simulation platform is it is very hard to collect crash information. But we had some ideas ongoing about extracting, for instance, like crashing episodes from videos. But that's a valid question. That's a valid point. I agree.
Thank you. Maybe I have 1 minute to have another question. What is the relation of your work with the surprise adequacy criterion metric that is presented before the last year ICSI? It is also a measure of unexpectedness. Can you answer this question?
Right. Yeah, surprise adequacy can be used as to measure like the distance from the training distribution, and particularly it is interesting to apply to this to this case study because it is a white box metric, whereas like the score of the Half encoder is a black box metric. So it would be particularly interesting to compare the two and see which one is the best. That's a good suggestion.
Okay, thank you for the nice presentation and good answers again. Thank you, Andrea.
Thank you.
Okay, let's move on to the fourth talk in this session. The title is Approximation, Refinement, Testing of Computer-Intensive Cyber-Physical Models, an approach based on system identification. And this talk is presented by Claudio Menghi.
Thank you for the introduction. So as mentioned, the title of this work is Approximation, Refinement, Testing of Compute-Intensive Cyber-Physical System Models, an approach based on system identification. I'm Claudio Menghi. This work has been developed in collaboration with Shiva Nejati, Lionel Briand, and Iago Isasi-Poracche. Let's start from the problem definition. So our high-level goal is to help engineers in developing cyber-physical system models. Our specific goal is to help engineers in developing industrial models of CPS. So industrial model or cyber-physical system are often compute-intensive. A compute-intensive model requires hours to complete a single simulation of the model under test. This is the usual case in industrial settings, since compute-intensive models are usually complex and include many components, often developed by third-party companies. For example, a single simulation of our case study, a real-world satellite model provided by our industrial partner LuxSpace, requires around 1.5 hours to complete a single simulation of the model under test. Now, classical testing techniques require to simulate the model under test a high number of times to detect failures in the models. When classical testing techniques are applied to compute-intensive cyber-physical system models, those techniques require an enormous amount of time, to the extent that using these techniques for those type of model is impractical, if not even impossible. Therefore, classical testing techniques fail in handling compute-intensive cyber-physical system models. The goal of this work is to develop a testing approach that can effectively and efficiently handle compute-intensive cyber-physical system models. Our approach is called ARISTEO, Approximation-Based Test Generation. The input of ARISTEO is a model under test that is compute-intensive. The first step of ARISTEO is to compute an initial surrogate model, which is an approximation of the original model under test that is faster for being executed and simulated. The approximation activity is represented in this slide within the approximation block. The surrogate model is then used as input for the subsequent testing activity. The testing activity is represented in this slide within the falsification box. During testing, many test inputs are evaluated on the surrogate model. And this is possible since the surrogate model is usually fast for being simulated. The output of the testing activity is a single test case that is likely to show a violation also on the initial model under test. Then this test case is executed on the original model under test, and the test case is verified. And essentially, the goal here is to check whether the test case is revealing a failure also on the original model under test. If this is the case, the failure is a real failure and is returned as output by RSTO. If this is not the case, the test case is showing a spurious failure, since the test case shows a failure on the surrogate, but that is not a failure on the model under test. Therefore, the surrogate model needs to be refined. The refinement activity is represented in these slides within the refinement box. The refinement box aims at refining the original approximation, the original surrogate model, to better mimics the dynamics of the original model under test. After the refinement activity ends, the loop is repeated. RSTO ends with whenever a real failure is detected or whenever a time budget is exceeded. We implemented RSTO. For the falsification and the checking activity, we relied on falsification-based testing techniques. Specifically, we had used Staliro, since this tool has been classified as ready for industrial development. For the approximation and refinement activity, we had used system identification. System identification provides a set of techniques that allow learning from data, input and output data, an approximation of the original model under test. We relied on the MATLAB system identification toolbox for this part. The final tool is provided as a MATLAB standalone application and is made publicly available. To evaluate our tool, we check the effectiveness of RSTO. Specifically, we check how effective is RSTO in generating tests that reveal requirement violation. Furthermore, we also check how efficient is RSTO in generating tests that reveal requirements violations. To answer these questions, we had tried to compare RSTO with Staliro. Doing this comparison on compute-intensive cyber-physical system model is impossible for two main reasons. First, compute-intensive cyber-physical system models are not easily accessible. The models developed by academic researchers are usually not compute-intensive, and the ones developed by companies and real industry are usually not easily accessible. But more importantly, this is impossible due to the time that would have required to run such experiments. For running the same experiments we are discussing in our evaluation, it would require us several years of computation before providing any statistical significant result. Therefore, for this comparison, we rely on non-compute intensive cyber-physical system models. Our results show that, on average, RSTO was able to detect almost 24% more requirements violation than Staliro. Furthermore, RSTO was also, on average, more than 31% more efficient than Staliro. To complement the results obtained by research question 1 and research question 2, we consider an additional research question, which is how applicable and useful is RSTO in generating tests that reveal requirements violation for industrial compute-intensive cyber-physical system models. For answering this question, we used the original model of the satellite provided by our industrial partner LabSpace, and we ran both RSTO and Staliro within this model. Our results show that RSTO was able to detect requirements violation within 4 hours, basically by simulating the original model under test only twice. Staliro was not able to detect any requirement violation within the same time budget. Therefore, we conclude that RSTO efficiently detected requirement violations in practical time that Staliro could not find on an industrial compute-intensive cyber-physical system model. To conclude, we defined and implemented RSTO, an approximation refinement-based testing approach for compute-intensive cyber-physical system models. We had compared RSTO with an existing tool for cyber-physical system coming from the literature, And our results show that Aristeo can indeed effectively and efficiently handle compute-intensive cyber-physical system model. Furthermore, we were able to detect problems on a real industrial model coming from our industrial partner. Thank you for the attention. We are available for answering any question.
Okay, thank you for the nice presentation. I think this is very interesting talk, and we have several questions from the audience. The most voted one is, the initial surrogate model is trained before using it. Did you take accuracy of the surrogate model into account?
Yes, the initial surrogate model is, so there is a first execution of the original model that generates input and output data. And from those inputs and output data, the system identification tool is used to learn the surrogate model. Of course, like there is a relation, an accuracy of the surrogate model. On the other hand, we don't care too much on how accurate the surrogate model is, since our goal is actually the surrogate model is only needed to guide the search. So it's not necessary that the surrogate model is really accurate in predicting the output of the original model, while there is probably a relation between the two.
Okay, thank you. And so, maybe I can have one more question.
Specifically, sorry, to complement
yeah, please. Yes,
how
yes.
The model is, because as long as the surrogate model guides the search in the right direction, it's fine for us. Furthermore, it will be refined in later loops by Aristeo.
Okay, thank you. We have one more question. What can you say about ethical requirement violation? Are they taking into account your approach? Ethical requirement violation, yeah.
Oh, I do not get really what ethical means within this context. Maybe can you, I would ask to elaborate a bit more on this.
Yeah, I think, yeah, we are talking about something, I don't know. Yeah, let's keep this talk after the session with Jose. This is a question from Jose, so maybe you can contact directly to discuss about this question. Thank you very much again, Claudio. Thank you.
Thank you.
Okay, let's move on to the final talk of this session. The final talk is Comprehensive Study of Autonomous Vehicle Box by Joshua Nathaniel Garcia. Joshua?
Yeah, just okay. All right, thank you for the introduction, Dongwon. So one of the things that you will maybe start noticing from even the talks in this session is that autonomous vehicles, they are in fact becoming ubiquitous and pervasive. So autonomous vehicles, or also called self-driving cars, are being claimed by the companies that are making them to have already driven millions of miles and also have given thousands of rides on top of that. So of course, we're talking about cyber-physical systems. So they have both physical components and software components that interoperate and interface with the physical world. And as we've been discussing, such systems are easily safety critical. And the bugs, the faults, the defects within them can easily result in injury to people and other living creatures, and also loss of life, like this example here from 2018, which is in fact the first AV pedestrian fatality, which occurred in Tempe, Arizona. It involved an Uber AV, and it occurred around 10 p.m. at night. Sadly, the unfortunate victim was crossing the street, pushing her bicycle. The vehicle failed to detect her in time to stop. There was a backup driver who also failed to detect the woman, and sadly she lost her life. And so this is just one example of how these AV bugs are not well understood. Besides the fact that there's really no previous empirical studies of AV software bugs, we have a poor understanding of the root causes of these bugs, what kinds of errors may result due to these causes, or even what parts or components of the AV software system are most buggy or most affected. So one of the obstacles to performing such empirical studies has been the lack of industrial grade AV software systems, or at least researchers generally having access to such systems. Well, this is no longer such a problem due to the open sourcing of 2 production level AV software systems, Baidu's Apollo and the AutoWare software system. So Baidu is one of the largest AI and internet companies out there. And in fact, they've already reached a mass production agreement with Volvo and Ford. So expect to see more of their vehicles out there. AutoWare is backed by a foundation, which includes, for example, the US Department of Transportation. AutoWare has been adopted by that agency, and also includes a variety of major companies, including Intel, ARM, LG, and Huawei. So what our goal has been is to comprehensively study these AV bugs by looking into the repositories of Apollo and AutoWare. We studied over 16,800 commits. And as a result, we looked at nearly 500 AV bugs. We classified those bugs into 13 root causes, 20 symptoms of those bugs, and 18 different categories of components that may be affected by those different bugs. And based on that classification, we suggest future research directions in the area of autonomous vehicle software systems. So before I move forward, it's important to have an overall understanding of autonomous vehicle software architectures. So such a software architecture takes as input a variety of sensors, including LiDAR, radar, GPS, and so forth. So based on these inputs, the vehicle does some localization, identifies the position of the vehicle in the world. It detects objects and tracks them. It performs predictions based on that previous information in a high definition map. So for example, it determines future positions of obstacles in the world. It performs some planning, for instance, where to move the vehicle or the future trajectory of the vehicle, and supplies information to actuators, such as the steering wheel, brakes, and gas. On top of these components, there's also other major ones, such as the human-machine interface, for instance, a GUI to the system, and infrastructure components, such as robotics middleware. So based on a variety of commits, issues, and pull requests, we performed a methodology that involved an open coding scheme where we focus on closed and merged pull requests that involved bugs and fixes of the software system, which overall led us to filtering down to nearly 500 AV bugs. As a result, we ended up with the three-way classification of root causes, symptoms, and AV components shown here. So for example, 13 root causes included incorrect algorithmic implementations, numerical computations, and configurations. From the 20 symptoms that we identified, a variety of them were specific to driving functionality, for example, stopping and parking, speed and velocity control, and vehicle turning and trajectory. And we also identified 18 AV components that can be significantly affected by AV bugs. These include the components that I just previously described, but also its subcomponents. So based on that three-way classification, we studied 5 research questions. I'm going to focus a little bit on 3 of those research questions, starting with bug symptoms produced by root causes, and in particular focus on 2 research findings for this research question. In particular, incorrect algorithmic implementations that are specific to this domain. For example, they have something to do with algorithms involving perception, localization, planning, and prediction. They often involve many lines of code, so on average 100 lines of code or more, and they cause about 20% of AB bugs, or more specifically, 8 types of driving symptoms. These kinds of bugs are going to be difficult, for example, existing bug localization, automatic program repair to handle. So this is an interesting open research problem that is focused on from this finding. Another root cause that was particularly interesting in relation to bug symptoms here had to do with incorrect assignments of variables, conditional statements, or conditional logic. These simpler kinds of root causes, which resulted in about 25% of the bugs, only involved about 20 or fewer lines of code and caused about 16 of the 20 AB bug symptoms. So these kinds of bugs may be well positioned to be handled by existing automatic program repair techniques and bug localization. So another interesting research question I'll focus on is the frequency of bugs in AV components. And this question is particularly important because it can help researchers and practitioners focus their efforts on specific components for future research or for maintenance activities. So what I'm going to do next is I'm going to highlight the more buggy components of autonomous vehicle software systems. So in terms of more to middle to high number of bugs in components, we have perception, localization, and the HMI. I'm going to focus on perception a little bit on the top left because as maybe you're starting to notice by looking at some of the talks in this previous session, a lot of the focus of previous testing and analysis oriented work have to do with perception. One of the reasons is, for example, has a lot to do with machine learning and deep neural networks, and the number of bugs also justifies that. However, the most buggy components are in fact planning and infrastructure. And so planning in particular has the most number of bugs by a significant amount, 135 bugs in total. And planning is particularly interesting because most of the bugs in planning affect driving functionality, so about 62%. And what this means is that many of the bugs that can lead to driving errors, serious injury, and even death are likely to occur from planning. However, planning is one of the least studied components of the AV software system at the moment, but it's the most buggy and probably the most dangerous. So this is one particular finding that I'd really like to emphasize. So in conclusion, I've given you a little intro, a little preview to our comprehensive study of AV bugs and the taxonomy and characterization behind them. In our paper, there are about 16 major findings that relate to bug detection, localization, and repair. I've only been able to go over a few of them, so I encourage you to look at the paper. In our future and current work, we're focusing more on test generation and for AV software systems, in particular having to do with planning, and refining our bug data set for the purposes of automatic program repair. So thank you very much for your time and attention.
Okay, thank you, Joshua, for the great talk. We have several questions from the audience. The most voted one is from Jane. Last night, Nancy Levinson said that accidents are caused by flawed requirements, whereas you emphasize code bugs. Are your bugs potentially accident causing?
That's a great question. So in fact, what you'll find is that a lot of them in fact are. So if I go back to the previous slide, for example, all of these bug symptoms in planning have an overwhelming majority of them have to do with the actual driving functionality. And so a lot of them, for instance, involve, for example, stopping at the wrong time or even crossing the intersection at the wrong time. And so a lot of them, in fact, do potentially result in crashes. And by crashes, I mean crashes of the vehicle itself, not of a particular component.
Okay, thank you for the answer. I think this is the right time to end this session. Thank you again for your great talk, Joshua. Thank you. And thank you for all the presenters. We have a great session here. So let me close this session A1, Autonomous Driving Systems, and let's have enjoy the remaining sessions as well. Thank you. Bye.
Thank you. Bye.
And now it is over.
All right, hello everybody, and welcome to the session on cyber-physical systems. If you are viewing this stream on the ICSI Clouder platform, please enter your questions on the left panel throughout the talk. Don't wait till the end of the talk because it does take time for questions to appear. So let's go ahead and get started. First speaker is Dalal Al-Wajah from Imperial College London, and she's talking about adapting requirements models to varying environments.
Great, thank you, Joe. Let me just put this up. Great. Yes, so as I said, as Joe said, I'll be talking about joint work that I've done with Antoine Baekje and Axel van Lamsveert. So as we know, software often is designed to operate in particular environments. These environments can change over time and over space, but full knowledge of these environments is not always known at design time, especially as these can change due to anticipated, unanticipated events where new different services are needed for different customers or new regulations or standards are introduced, often requiring these cases software to adapt to such changes. Take, for example, the problem of designing an urban traffic control system for enforcing low emission zones. If we think about, for example, these systems that are often designed for environments where polluting vehicles like buses and goods vehicles are generally present, and in some cases it might be also considering cars and motorcycles. But the way that the LES is enforced can vary from one city to another. So if we take, for example, the case of London and Brussels, let's say. So a system that's designed for London, for example, should recognize that polluting vehicles are allowed in these LES zones if they pay a daily charge, and that charge depends on the vehicle type. So for example, the case of motor caravans, that daily charge might be £100. and that if the charge is not paid, fine must be issued depending on the vehicle type or the time elapsed since the fine was issued. So, for example, again, if you think about the motor caravan, it's £500 unless it's paid within 14 days, then it's £250. Now, a system like this couldn't be immediately deployed in Brussels, where it's assumed that polluting vehicles are not admitted, for example, and that the fines that are issued for those who enter nonetheless depend instead on the fuel type or the classification of the car, for example, the Euro standard, and if it's a repeated offence. So if the car operates on diesel and the Euro standard is of a Euro 1, then the fine is 150 euros for first-time offenders, but if it's a repeated offence, then it's 250 euros. Now, this work has been, this existing approaches aim to address this problem, but they can be classified, let's say, into three main groups: requirements adaptation, dynamic software product lines, and requirements evolution. The main limitation, however, is that they typically assume that the possible space for variation is known in advance, they're explicitly modeled and accounted for, and that if any changes are needed, then it'd be quite difficult to change. So they're quite, in a sense, and some of them it's fixed model of these adaptations. So what we present instead is a formal approach to requirements adaptation at design time, in which the adaptation process is instead driven by satisfaction arguments. And by that, I mean that low-level contextual goals achieve high-level common goals across, let's say, various contexts. And that the adaptations don't change necessarily, for example, that the adaptations are learned as new environment conditions become known. So they're not fixed or known a priori. And that the adaptations don't need to change requirements unnecessarily, just that they make local changes where needed and generate similar variants of the software where possible. And importantly as well, that we wanted, for example, that these adaptations of the requirements, that they adhere to software capabilities, so they are actually implementable once they're adapted to the new context or environment. So let's take, for example, the Les example that we've discussed before about the London context and the Brussels context. So to represent requirements, we adopt the goal-oriented modeling framework, CHAOS, which enables their formal specification and analysis. And for the purpose of the presentation, it's enough to know that requirements are modeled as goal graphs, that high-level goals are gradually refined into low-level goals until they can be assigned to individual agents, and that the children goals at any one depth within this graph are consistent. So for example, in this case, in the vehicle type charge and the fine set by vehicle that are highlighted in the graph are consistent, and that they entail their parent goal, in this case, that the charge paid when polluting vehicles admitted. What's important about these models as well, or what's a good feature about them as well, is that the dependencies on the environment conditions are explicitly captured. And in the setting, if we think about our aim of our work, the aim of the methodology is that for a given goal model of a particular source context, in this case, the London context, what we want to do is adapt the problematic requirements in this model to suit the Brussels context while preserving high-level common goals. So for example, what's common between these two models is the polluting vehicles should be penalized, and ensuring that the semantics of the refinements are correctly maintained once they're adapted. So I'll briefly describe our proposal, the key steps of our approach, which we call RESPIRE, for requirements adaptation varying environments. The details we've left, obviously, if you're interested, read the full paper. But first, what RESPIRE does to do the adaptation is build what we call a reference model. So that is built from, we take the goal model of the source context, the environment conditions of the new context to which we want to adapt, and the agent or software specifications in terms of their capabilities. So what we want to describe is, for every agent or component that we have of the software, what can they monitor and what can they control? So for example, if I look at the reference model that we have in the case, what we have is a root goal to be maintained across the two contexts. And we call this the anchor goal. And the refinements include, in this case, goals that are subject to adaptation, so in this case, the London goals, and where the source environment conditions have been replaced with a target context. The reference model is then undergoes an iterative adaptation process, and this is based on a counterexample guided learning loop in which adaptations of the reference model are learned from counterexamples to the model's correct semantics. So in this case, the first step is checking a model checking the model, and to make sure that the refinements are correct. So to trigger adaptation, what we do is verifying the semantics of the refinements in this reference model, which basically means we model check the sub-goals against their parent goals. So Respire, in this case, reduces the number of verification needed significantly by checking that the leaf goals on these goal graphs entail the anchor goal. And if a counterexample is generated, this illustrates an example of an anchor violation. So why this anchor goal does not hold in this new context. Now, to guide the adaptation towards similar variants, Respire also generates examples demonstrating how the original leaf goals could satisfy the anchor goals in the new environment. And any counterexample to that is an example of anchor satisfiability. So in the case of the traffic control system that I've talked about, the first check shows that the need for adaptation. So in this case, for example, a lorry running on diesel with the Euro standard that's less than 3 enters a less zone and is not issued a correct refinement. So in that sense, it triggers an adaptation. This tells us that there's a problem in the model, but where it is exactly and how to resolve it. So do we rewrite the specifications, the goal specifications, or do we change the refinement relations? And if so, how do we do that? In what way do we change the refinement links? Do we change the depth of the tree? Do we change the tactics of the refinements? So what we use is in Respire to answer these questions automatically through a process of logic-based learning. And this is a mechanism for synthesizing and revising logic programs from observations of what's true in the models captured by the program. So given a fixed theory, which we call a background theory, which is not subject to change, a revisable theory, which is subject to change, and that which together do not entail observations, the aim is to find a revised theory such that that entailment relationship holds. The solution space, we can constrain it by giving a language bias, so by providing information about the signature which can appear in the revisable theory, or constraints over the kind of relationships that can hold structurally between these different requirements. We can also introduce optimization objectives over these revisions to give preferences to ones over other ones. So to learn adaptations in our context, we define this background theory as constituting goal model semantics, the anchor goals, which are not subject to change, the agent specifications, and the new environment conditions, all those parts of this, the information that we have that won't change. And what we give as our revisable theory are the goal specification and the refinement relationships. And as our examples, the traces that we've generated, so the anchor satisfiability example and the anchor violation traces as examples that should hold in the models and should not hold, respectively. And the adaptation space in this case includes sets of new goals and specifications and refinement relationships that form the adapted model. To search for the similar variants, a cost is incurred for every addition and deletion to the goal specifications and relations. And to find local adaptations, we also add a cost for changing goals that are further apart within these models. And then the model, this is determined by how many refinement links are connecting them. And the learning mechanism tries to minimize these costs. So in an example, the learning generates a candidate adaptation, which issues a fine for any vehicle running with the Euro standard entering the area. Then in this case, that is a first example, and the process iterate, it checks whether the leaf goals satisfy the anchor goals. In this case, it triggers an adaptation because it's not satisfied. And then the process continues until adaptation is triggered, and by that ensuring that the construction of an adapted model that's semantically sound. However, the goal model could still contain irrelevant goals, for example, talking about charges, daily charges. And through that, what we do is we can eliminate that through a process of minimization in our procedure, which is detailed in the paper. So to evaluate the Respire experimentally, we built a prototype tool in Python, which builds on third-party modules. The tool keeps the engineer in the loop to validate the anchor satisfiability traces, since these will be allowed by the adapted model. And we've considered 6 variants of a computer-aided dispatch system, focusing on 2 contexts and adaptations in both directions. And what our results have shown is that in all cases, RESPA was able to compute similar and local adaptations, with only a subset of the goals needing adaptation. Minimization removed irrelevant goals, and longer iterations for adding refinement relations compared to deleting. But we need further empirical analysis to understand the correlations between adaptation strategies, number of intermediate adaptations computed, and the final cost. But generally, we find that the adaptation was compute time was relatively small and could be improved. So to conclude,
you have less than 1 minute.
Oh, yeah, okay. So just to conclude, recurrent adaptation approach that we provide is driven by satisfaction arguments, and where the adaptation space is not explicitly defined, and the adaptations are local and similar. We've built it using a counterexample guided learning approach, which considers quantitative objectives, and our extensions are looking at runtime, which integrate controller synthesis and allowing systems to degrade when adaptations are not found. And thank you very much.
Thank you, Dalal. So a really quick question, because we are short on time. So you've done the one study between the London and Brussels and looking at the adaptation in both directions. Are you looking at other studies?
Yes, we're looking. Yeah, we're basically looking at case studies by which we're trying to gather from various different literatures. So at the moment, we've got amber bus controls, which we're getting more from reactive synthesis literature and robotics. And yeah, I mean, we've not included that in paper, but that's part of our ongoing work on that.
Excellent. Well, thank you very much, Dalal.
All right, I'll stop sharing now.
So next speaker is Alessio Ferrari from CNR, and he is going to be talking about comparing formal methods for system design, a judgment study.
Hi, can you hear me?
Yes.
Great. So thanks for the introduction. I am Alessio, and I'm presenting you this judgment study on comparing formal tools for system design. And here are my colleagues from PISA. So here you have the paper in one slide. We are speaking about formal methods and tools and application in the railway domain. The problem is that there are lots of studies on applications of a single formal tool to a railway problem, but there is little comparison between tools. So tool selection is quite difficult for companies. Therefore, we performed a judgment study with 9 tools and 17 experts to compare the tools. The result is that we have now a table indicating when to use a certain tool and what are the typical problems that companies may encounter when using a certain tool. And the main contribution is the emphasis on tool diversity, formal methods diversity in railway, because each tool is appropriate for a specific railway development context that depend on the phase, the type of system, the user background, and other factors. So let's take a step back. What are formal methods? Formal methods are mathematically based techniques for specification development and verification of systems. They are normally supported by formal tools, and in railway safety critical system, formal tools are highly recommended by the norms. So if you are a company, you would like to use them. The problem is there are more than 100 tools, both commercial and academic ones, free ones, and they have different features and also different languages, as you can see from this picture. So as I said, which tool to select is a very difficult question. That's why we started this project, which is an European project called Rail. Main tools that are for railway. report their reflection on when to use a certain tool and what are the issues encountered. Other two experts, two analysts, when I say experts, I mean experts in both the tools, the formal methods, and railways. So the expertise is in these two fields. And the analysts took the information from the designers and produced a preliminary evaluation table, which was later assessed by external assessors. And the final product of this analysis is this evaluation table. As you can see, is very synthetic because it is oriented to railway practitioners and especially to low and middle management for decision making. And what you can see from this table that you can read more, dedicate more time for by reading the paper, is that you can see that the different tools have served different purposes. They can be applied for different systems, Another aspect that emerged was the several issues that each tool has, and are mostly related to the graphical user interface, the support for parallelism, and the difficulty of handling the language used that require several different backgrounds to be used successfully. Here you have the implication for practice and research. The implication for practice are the green one. So we are providing indication to low and middle management of railway companies. And the two elements that emerge as most relevant from this study is the relevance of formal methods diversity. So several tools are required to address all the needs of the railway process and all the phases and all the purposes. And we also need expert diversity, because each tool requires a high degree of expertise to be software engineering, and we think that the framework of the study, the approach can be, the method can be used whenever you have to perform a study where human subjects must be experts, you don't have many experts available, and you need an hand-on activity for triggering reflection by the experts, and you are still at the exploratory stage. And finally, another aspect that emerged is related to the human aspects of formal design, because we saw that subjectivity plays a crucial role even between the experts. There were disagreements on things that would seem obvious, like the support for parallelism. We saw that the relevance of the background of the different experts really affect the judgment, and also the subjective preferences play a role in the judgment. For example, preferences for a textual language over a graphical language. So as conclusion and ongoing work, this is a first judgment study on formal methods applications to railways, and our results point to novel research direction, which are mainly tool and expert diversity and human aspects of formal design, because formal methods are also about people and not just about mathematical formulas or temporal logic formulas. Other work that we are currently performing, that we performed actually after the project, is related to the Desmet evaluation, so the systematic evaluation, a usability analysis involving practitioners, and the actual combination of different tools for a large model. And currently, we are involved in this 4-second array project, which is a follow, benefit analysis of introducing formal methods in railways. So if you have any questions, here is the summary of the most relevant slides.
Very nice. So thank you, Alessio. There is one question.
That's really interesting. I wasn't there. I wasn't there yesterday. For human aspects of safety study, I cannot say too much as I know. But I would emphasize the role of the designers, the actual person who is involved in doing the safety assessment and in doing and using the actual tools that are used for in the process of safety assessment. So there is for sure a relevant aspect in this. As of course, in the safety culture, you already consider the subjectivity in some way because you always involve multiple people in the same activity. No, you have diversity in practice. But this aspect, for example, in the actual studies is not considered so much.
All right. Well, thank you very much.
Thank you.
So next up is a demo from Shafil Hasham Chaudhry from University of Texas at Arlington. And the demo is SLEMI finding Simulink compiler bugs through equivalence modulo input, EMI.
SLEMI, Automated Compiler Bug Finding for Simulink. When designing complex cyber-physical systems, engineers design graphical models to simulate them in commercial tools like Simulink and even generate code to deploy in target hardware. Now, a bug in the toolchain can introduce further bugs in the artifacts they automatically generate. And we don't want safety-critical systems to fail due to compiler bugs. So we need automated tools to test Simulink. State-of-the-art tool SL Forge automatically generates valid Simulink models in order to test Simulink. It's inefficient, however, since generating a valid Simulink model from scratch is very slow. Our tool SLEMI is first of all fast, since it just introduces small changes to an existing Simulink model instead of trying to generate a whole model from scratch. It also found more bugs than SL Forge. We gave the two tools similar resources. When SL Forge found 2 bugs, whereas SLEMI found 10 bugs in various Simulink versions. We use EMI, short for Equivalence Modulo Input, which takes a Simulink model known as SID and automatically create a mutant such that they are functionally equivalent when we compile and simulate them in Simulink for some input I common to both. SLEMI has 3 independent components. First, a framework to run experiments on Simulink models, such as pre-processing the seed models to improve overall runtime. Next, we create EMI-based mutants from these seeds. Lastly, high-performance differential testing to compare the mutants with their seeds. Any difference we find is likely indicator of a compiler bug. All of our tools are open source and require MATLAB version 2018A or newer. We start with the experiment framework, which scans for seeds in a distributed file system or in a local file system to pre-process them in parallel and caches intermediate results, such as coverage, data type, and sample time of every block in a seed. Using this information, we then perform several one-time base mutations per seed, which further improves overall runtime. Our EMI component then consumes this cache and generates multiple mutants per seed in parallel. Lastly, our differential testing component compiles, runs, and compares mutants with their seeds again in parallel. To launch a tool, use command line or MATLAB's graphical user interface.
Hello, my name.
All right. So thank you. Unfortunately, there's no time for questions for the demo presentations, but I encourage you to reach out to the authors if you do have questions. Next up is Andrzej Wazowski from IT University of Copenhagen, and he's going to talk about the forgotten case of the dependency bugs on the example of the robot operating system.
Hello, I hope things work. Thank you for coming to my talk. I'm kind of reflecting on what's going to happen now. I've been listening now for an hour and a half to amazing talks about challenges in cyber-physical system development, in autonomy, machine learning, all these things we should really be working on so to make to move the society forward, right? And what I'll be talking about is a little bit like a talk of shame, because it's a talk about what we should have been doing for years, and we haven't done it, and now we're left with the problem. So my story is kind of similar to many others here, at least in the beginning. I got myself involved into a project with robotics community, and I was planning to work on some amazing challenges in automated planning, in navigation, in localization, in perception, knowledge representation. I thought, okay, this is going to be fun, all these testing challenges, etc. Well, that's not what happened. We started with a preliminary assessment of the state of the art situation. Our subject was the robot operating system community. The project is with one of the associations that is stewarding those. And we did an assessment of what are the quality assurance or quality challenges in robot operating system. And what we have found was not all these exciting things, but was this. So what is this? This is just one example of what we have found. It's a problem, a simplistic or simple problem from an actual history or from a released code. This is from a driver for a universal robot arm, although it's not implemented by universal robots for all the transparency. Universal robot arm is an industrial robot arm, probably one of the most popular robot hardware components that you see in all sorts of robotics labs around the world. So this is a problem taken from the driver itself. On the left, we have a build script. The build script introduces a dependency in the driver on the boost library. Boost library is like a standard library in C++ that also people are using. So on the right, we have another build script about an extract from what is called let's call it a package manifest. So a piece of specification that tells the package manager how to wrap the whole thing together and how to deploy it. It says what the package provides and what it depends on. And typically in most systems, these are separate for very good reasons, which I won't discuss now because I don't have time. So the problem is that the package manifest in this particular example doesn't have this red line here, run depend boost in the bottom. That red line I have injected to show how the bug was fixed, which means that when the package builds correctly using the script on the left, and then it's packaged using the package manager using the script on the right, and then someone installs it, there is no guarantee that the boost library will be installed. Now, if the user runs the driver, what happens is that if the boost library is not installed, the dynamic linker will fail and the node will not start and the ARM will not operate. Well, this bug was actually found in released software. How did it make it so far? Well, the person who has been developing this is a C++ programmer, so he had the boost library installed on his system anyway. You do that. You do that if you are a C++ programmer. People who are reviewing his code and testing it, they are also C++ programmers, so they also had the boost library installed. Worse, the continuous integration system even had this boost library installed because something else required it, and it only took a weird user who was doing a parsimonious robot configuration to discover this problem. So it is in a way a case of all the old works on my machine problem and not a particularly complicated one. We have looked largely at those bugs and we have identified this problem appearing a lot, not just this problem between dependency between the build script and the package deployment, but in general, composition problems between software artifacts. So we decided to run a study, and from that study, the following definition of a dependency bug emerged. Dependency bug is a fault that appears, that has sort of two qualities. It has a failure, so it manifests itself when accessing an asset that is unavailable, either because it doesn't exist, it's located elsewhere, or it's broken in some way. And it also has a fault. So it's not a bug in an algorithm or in the logics of software, but it's a bug that can be fixed by modifying how the software has been composed, configured, linked together, etc. So dependency bugs, kind of what Andrzej is telling us, they are silly, right? Easy to fix. If you're a package author, you see the error message, oh God, I forgot to release boost in run dependencies, right? also, they are rarely experienced by the authors of the package because things usually are configured correctly on their machines. I asked once one of our colleagues in the community about this problem, and there's like, oh, that's something researchers don't really like to work on. This is others people plumbing problem. That's, you know, you don't get to fame working on that. On the other hand, they are unbelievably complex when you're a newbie, when you're a newcomer to a project. You get an error, it means nothing to you. It's an error in someone else's code. You have no idea whether you made something wrong or they did it. So they are a barrier of entry for new people to the projects. And actually, it's a very common barrier of entry in ROS, as you will see in numbers soon. So there is another reflection here. Lots of people in this community, including myself, work on methods to make software more maintainable, reusable, evolvable, I don't know, component-based development, model-driven development, software product lines, you name it. They're all technologies that seem to help the software evolution at large, but they do come at a price. The price usually is introducing yet another configuration or composition mechanism that might fail at runtime. So the dependency bugs is something that we're introducing in a way to the software engineering universe. We're kind of responsible for it, but it also takes away from the value of what we are producing as researchers. So in this work, we have run a qualitative study of these dependency programs in ROS, and produced this taxonomy. I will not go through it. I just want to make sure that you understand that there is much more to it than dependencies between build scripts and deployment mechanisms. There is actually many times they appear in almost all phases of life cycle of a piece of software, and the dependent artifacts, they can be of very different kinds. Are these dependency bugs really a big problem? We have been doing a sweep study of bugs in ROS based on GitHub repositories, and intuitively they felt too many. So we started to measure the same. We've run a very simple classifier, just checking on string completion how many of these bugs might be dependency bugs. And we found that in ROS melodic repositories, 16% of bugs, very approximately, are dependency bugs. That's a lot, I would say. Bugs in general are extremely rare events, and they are in very many categories. If 16% of bug discussions contain some mentions of dependencies, that's a problem, I think. Well, we thought maybe ROS people are not quite smart. They did something wrong or whatnot. Well, I hope nobody from ROS is listening here. So we decided to check other GitHub projects. We went to top 30 GitHub projects. This number was 14%. That seems to be a very common problem. And very quickly, we did a back of the envelope, very quick classification that seems to indicate that this is on par in the same sort of ballpark category as concurrency or memory errors. Well, whereas there is lots of research on concurrency and memory errors, and dependency errors, yeah. So 53% of packages affected, 53% of packages in ROS are affected by dependency bugs. 30% of contributors to ROS participate in discussing these problems. So the dependency bugs attract lots of discussions. In fact, they attract most of the contributors to any package that experiences them. Average discussion duration for dependency bugs is 4 posts plus a standard deviation of 4. This is actually longer than an average discussion for non-dependency bugs. This can be explained in many ways. Maybe these discussions are easier to get into, more people are opinionated, but that's not important here. What's important here is that lots of people, and especially senior members of the community, are using time on this, and they could be using this time on something else. The senior members in the community are the scarce resource for sustaining an open source project. These statistics that I was showing to you, they are plainly based on GitHub discussions, but in ROS, lots of discussions happen on ROS answers, which is the Stack Overflow of ROS, and this is not, I didn't even touch on this, but you just open ROS answers and with tons of dependency problems, just sort of anecdotally. Aiming for a conclusion now. So dependency bugs are relatively simple. I would call them simplistic, yet the ratio of annoyance to simplicity in these bugs is unbelievably high. It's an offense to the community that they still exist, that we still have to suffer this and spend 15% of our resources on handling them. They diminish the value of what we are doing as a software evolution community. They seem simple, so maybe they're eradicatable. Can we get rid of them somehow? With this, I'd like to finish. Thank you.
Thank you, Andre. So a question. So there's a big disconnect between the simplicity of the error that you're talking about, these dependency bugs, and the expense and time it takes to discuss them. And so what are people talking about? Are they blaming each other for the bug, or are they having a hard time figuring out what needs to be fixed because the fix is distributed over multiple modules?
That varies a lot, but in general, discussions are fairly efficient because experts get involved and they immediately see what's going on. And that actually what tells me is that these bugs are probably easy to fix. It's not like an algorithm problem you have to think a lot about. And you have like two ends, one is wrong, one is correct. So there is something to go by to find a heuristic to fix it. It's just they often appear between languages, so we almost have no tools that can fix problems between two different languages or formats. Everything is sort of in silos of language technologies. Yeah, it's a little bit harder when the error appears because another piece of software we depend on has evolved somehow, and we might not have competence. That takes longer.
And there's a second quick question. Do those dependency bugs have a common root causes, or do at least some of them have a common root cause?
We have looked at causes. There is actually a dozen of different causes, and so some of them are like the example I've shown was the leak of the assumptions about the developer configuration to the sort of final software which doesn't perform this, carry these assumptions, but there are many that are caused by coevolution of various components. And it's extremely difficult in a system so highly modular like ROS to make all these components evolve completely in sync. So often things break because someone else has changed some code somewhere else.
Right. Well, Andre, thank you very much.
Thank you.
So next up, we have a second demo by Sergio Garcia from Chalmers University of Gothenburg called Promise, High-Level Mission Specification for Multiple Robots.
Hello everyone, my name is Sergio Garcia, PhD student at the University of Gothenburg, and today I'm presenting my study, Promise, High-Level Mission Specification for Multiple Robots. It is foreseen the increment of inclusion of robots in our lives in the near future. Imagine a near future environment like a hotel or a warehouse where a team of service robots, a type of robot that performs useful tasks for humans, may interact to provide services such as object handling, transportation, or pickup and delivery operations, as is the example of Amazon warehouses. These tasks or missions must be specified and commanded by users who are in need of appropriate tools for such process. In order to tackle this need, we developed Promise, which is a domain-specific language with the aim of specifying missions to teams of robots in a simple yet expressive way. It was implemented as a plugin for Eclipse, and it is integrated into a framework. Promise provides both a textual and a visual editor for the user to specify the mission, but we will focus on the visual representation in this presentation. This language contains a set of atomic tasks that can be executed by robots, represented by color circles, and a set of operators that allow the composition of these tasks in complex missions. We conceived 7 operators, but I'll explain only 4 of them with this illustrative example to keep it simple. More details about these operators can be found in the paper. The parallel operator, which is always the root of the mission, decomposes the global mission into local robot-specific missions. This means that all the operators related to each branch will be automatically delegated to that robot, as represented in the labels of the edges. The mission associated with an event handler begins with the execution of its default mission and will not finish until this by default mission is finished. Atomic tasks are delegated to robots using a delegate operator that can be configured using parameters. The robots may interact or detect events occurring in the environment. If, while performing its by default mission, a robot detects an event that matches the one associated with the event handler, the corresponding behavior will be triggered. In this case, Robot 1, while patrolling a set of locations, detects an object, will request help to Robot 2. In a similar way, Robot 2 will wait idly in L4 until help is requested. If so, it will then trigger the sequence operator, which executes a set of operators in sequence. Robot 2 will then visit a location, grasp an object, and drive to L2. Thank you very much for your attention. If you are interested, please check the provided link to the repository of the tool or send me an email. Bye.
So yeah, so if you do have questions, I do encourage you to reach out to the authors. All right, so last presentation will be given by Ivano Malavolta from Vrije Universiteit Amsterdam, called How Do You Architect Your Robots? State of the Practice and Guidelines for ROS-Based Systems.
All right. Thanks for the introduction. Can you see the screen? It's loading.
I said we could. We did. Now we can again.
Okay. Can you see that now?
Yes.
Okay. Thanks for the introduction. So this work has been carried out in collaboration with the Vrije Universiteit Amsterdam and Carnegie Mellon University. The title of the work is How Do You Architect Your Robots? State of the Practice and Guidelines for ROS-Based Systems. So yeah, it's another work on ROS. The main drivers of this research are basically three. So the first reflection is that one of the main barriers in robotics is at the software level. So let me explain this. The idea is that we are seeing a lot of advancements in mechanics, in electronics, and other domains related to robotics. But really, when we are thinking about robotics today, we think about the intelligence that we are putting in it. And when we talk about intelligence, we are mostly moving towards the software area. Okay. The second reflection is that robotic systems today are getting more and more large and complex. As Andrei introduced before, now a robotic system is not simply composed of a couple of bundles or a couple of components. It is composed of tens, sometimes hundreds of packages and components with dependencies, of course, which can break, as we saw before. And basically, these kind of systems are really developed now by different groups, different teams, different companies, and then at some point you plump them together into a working system. So now we can see that if software is very important and the system is becoming very large and very complex, this means that at some point we will need some reasoning at the architectural level. However, what is happening now is that there is very little guidance about how to design robotic systems at the architectural level. So this means that now building a robotic system is still a kind of, let's say, craft type of activity. So what we want to do in this study is to observe what developers are doing when they work on their own systems. So we want to look at the real systems that have been worked by teams of developers. We want to extract from these systems what we call design stimuli, which are basically, you can see that as design concerns, and the corresponding applied solutions. And then what we want to do is we want to build a catalog of guidelines about how robotic software can be architected in such a way that it satisfies the classical quality attributes like maintainability, performance, safety, and so on. Okay, the study is, we have three main research questions for this study. The first one is, what are the architectural relevant characteristics of open source ROS-based systems? Again, we are looking at GitHub repositories. And here we want to look at what is existing out there. Okay, what are the existing systems that have been developed in ROS? And this can be used by practitioners for getting some examples about how other systems are implemented and some examples of documented architectures. Researchers can see this answer to this research question as a snapshot of real-world robotic software, how it is implemented in the ROS area. The second research question is about the quality requirements that are considered when architecting ROS-based systems. And again, practitioners can use this answer for understanding which quality requirements are impacted the most when working at the architectural level. And researchers can use this research question for getting some directions about future studies relevant for practitioners. The third research question is about how to guide roboticists when architecting ROS-based systems. And here the idea is to benefit practitioners by providing a catalog of guidelines for architecting ROS-based systems. And this same catalog can be used by researchers as a foundation for developing new approaches to better architect robotic systems. Okay, the study has been designed as in 2 phases. So the first one is by mining software repositories. So we started from a set of quite a large set of open source repositories, ranging from GitHub, GitLab, Bitbucket, and so on. And then out of those open source repositories, we applied kind of classical MSR pipeline, and we ended up with 335 repositories. We extracted some architectural data from these repositories by looking at Markdown files in the repositories, all their external links, and all the documents stored within the repository. And then we analyzed the data by applying a collaborative open coding for the first 2 research questions and thematic analysis for going deeper and extracting the guidelines. This led to a set of preliminary results, mostly demographics data and some more information about the types of the systems, and a preliminary set of guidelines. There were 39. Then what we did is we closed the loop towards practitioners. So in phase 2, we did an online survey targeting 520 contributors of these repositories. We collected 77 field questionnaires, and then we extracted the data and we analyzed it in order to complement the preliminary results of phase 1. Okay, as a, let's say, byproduct of this study, we built a dataset of real-world robotic software systems, and this dataset is fully available in the replication package of our study. So future researchers who want to do some further studies on existing and real robotic software, the dataset is here, so you can check it in the paper and dig it and play with it. Okay. Due to time constraints, I will just show to you a selection of the main results. Of course, in the paper there is much more. So the first thing is about whether developers are actually documenting the software architecture of a robotic system, and the answer is sometimes. So here we classified repositories based on whether they partially documented the architecture, meaning that we can have, let's say, an informal idea of the architecture of the system, or when we say yes, we mean that by looking at their documentation, there is a clear idea about what the architecture looks like. We know what are the main modules, we know how they communicate, we know what are their interfaces, and so on. But for the majority of the cases, we see that basically there is no architectural documentation in robotic software, at least at the moment. Okay, these are some examples of documented architectures. As I said, they range from very informal architectures with blocks and lines. They tend to use layered architecture notations, and they use this strange representation that you see on the rightmost part of the slide. Basically, this is quite recurrent because this is called the computation graph in ROS, and this is basically automatically generated from a running system. So here we can really touch concretely one of the advantages of having automation in software engineering, that is you can get for free some representation of the system on which you are working. As part of research question number 2, we analyzed the repositories in order to see what are the quality attributes that are more mentioned in those repositories. And here we can see a kind of ranking. So we have maintainability as the top one, followed by reliability, performance, usability, and so on. And in the survey, actually, this ranking is more or less confirmed. I refer you to the paper to look at the details about this. As for research question number 3, which is the last one, we extracted a set of 49 guidelines over a total of 7 families. So the families, you can see the families as a way to group guidelines based on the concerns that a developer may have. Like if I need to focus on how modules communicate, I look at the first type of family. If I need to look at how nodes' responsibility should be split, I look at the second one, and so on. This is an example of guideline. Here we are focusing on stateful nodes in the system, and the idea is that the behavior of each node should follow a well-defined life cycle, which should be queryable and updatable at runtime. Well, this guideline is important because per se, ROS, that is the platform that on which robotic systems today run, doesn't mandate any specific description of the behavior, or it doesn't require that the nodes follow any specific behavior. So basically considers nodes as black boxes, okay? However, we know that this may impact the overall quality of the system in terms of reliability. For example, if I don't know what is the current state of a node, then I may have problem in knowing what is happening internally to this node. Okay, and in the current repositories that we analyzed, basically developers were doing two strategies for implementing this guideline. The first one is to include a description of all the possible states of the nodes in documentation, in the documentation of the system, or they were mandating by design that nodes should always follow a fixed behavior at runtime. Okay, so I won't go. Yes. I won't go very much into the details about this, but you will see the guidelines in the paper. As future work, we are planning to build on this paper and on the dataset to mine architectural tactics for developing robotic software in order to target relevant quality attributes like safety, reliability, and others, with respect to, and especially to energy efficiency. For energy efficiency, we are also designing, and actually we are in the process of executing empirical studies, so experiments on real robots for seeing if actually the tactics that we are extracting at runtime, they actually bring to some improvement in terms of energy efficiency. Okay, as a summary, we are in the domain of robotics. So we know that software is the barrier. We designed the study by following two phases: mining software repositories and online survey. We built the dataset and we extracted a set of 49 guidelines for architecting ROS-based systems. This closes my presentation.
Very nice, Ivana. Thank you for the presentation.
Thanks.
So quick question. So you're talking about software architecture, but you're talking about you're reaching out to developers and practitioners. You know, do you know that you're reaching out to actual software architects? You know, are there roles being played on these teams of an architect?
This is a very good question. In this study, we focused basically on all the contributors of these repositories. So we were assuming to have a flat, let's say, organization. I think it could be interesting to see if there are some kind of roles within these repositories. I know that from other studies, for example, there is the concept of elite developer. So in this case, an elite developer may be seen as a kind of a proxy of a software architect. But in this study, we didn't do it. So we basically contacted all developers that were contributing to the repositories.
All right. Well, thank you very much. And thank you to all the speakers this session. So this does close the Cyber Physical Systems session. I encourage you to stay around in the room. There is a live coding session next, I think. All right. See you at ICSI.
Thank you.
Thank you, everybody.
Bye-bye.
It seems that there was some problem with my presentation, but did you hear it at least?
We were on Zoom, so I think if there were problems, I think they might have been encountered in Clouder.
Okay, okay.
Yes, everything was fine in Zoom. Amir, I think there was some glitches, right, with the sound with Alexia, right?
you.